So the next speaker is Thurau. And Christian is a data scientist at the Unbelievable Machine Company. That's one of the sponsors of PyData. It's a cloud service provider located in Berlin. And before that, he co-founded a startup in game analytics in Copenhagen. And he's going to be talking to us today about low-rank matrix approximations with Python.
Thanks a lot for the introduction. Thank you. All right, so first of all, the question, who of you does know what a low-rank matrix approximation is? Could you please raise your hand? Okay, most of you. Who does not know what it is? Okay. Who doesn't know what k-means clustering is or has heard of it? And okay, perfect, that's great. And PCA, principal component analysis, perfect, great. So at the end of the talk, I hope you will all see it in a similar way as I do it, that k-means clustering is also just a matrix approximation. So that's also one of the key conclusions I think of this talk. Anyhow, so let me start with what to expect in the next, say, 30 minutes. So first I will start with a brief introduction into what a low-rank matrix approximation is, what matrix factorization is, and then I will concentrate a bit about on the different methods that exist. So there's a huge amount of different methods. Obviously, I cannot talk about all of these, only on a very small amount of them. And I will also talk a bit about the implementation in Python of these. And then I will conclude with a couple of examples and some conclusions. So first of all, observation. So data matrix factorization has become a super important tool in many different fields. So you can see a lot of examples for this over the last few years. For example, when you have a look at the ratings of movies. So there they usually have a matrix in which you have in each row, for example, a movie, and in each column you have a user and its ratings. So if you think about that matrix, it's a huge matrix, and by itself you can't really make that much use of it. But then what you often try to do, you try to sort of factorize it or approximate it to extract some meaning out of that matrix. And there are a lot of other examples, gene expression data, digital images. So you can store images in a matrix by having in each column all the pixel information of the image, and then each row, so each column, and well, then each entry corresponds to the color value of one of the pixels. And in the columns, you have all the different images. So, and obviously graphs too, so you can store all information from a graph into an adjacency matrix. So, brief introduction. So what is matrix factorization? So let's assume you have a matrix V. And the goal of matrix factorization is actually very, very simple. So the only thing that you want to do is you want to find two matrices, W and H, so that you can approximate your matrix V by the dot product of W and H. So that's it. And then obviously for a lot of different applications and methods, the rank of W and H might change. But this equation here, this is actually all the basis of matrix factorization. So why the heck would you want to do that? Why do you want to represent some large matrix by some possibly lower ranked matrices W and H? So there are a couple of interesting things you can do with the matrix factorization afterwards. So two of the things I want to talk about in this talk. The first thing is that you can transform data by doing that. So that seems sort of obvious as things. So first you have the large matrix, and then you factorize it into two lower ranked matrices. So somehow you transform the data, and later I want to talk about what the benefit of this is. And you can also compress data. So if the rank of the matrices is lower than the rank of the original matrix, obviously you sort of lose some information, or you compress data. And then afterwards, you can always use these factorized matrices for example, information retrieval, pattern recognition, data mining. So this is really one of the first steps you would always want to do when you're dealing with huge data or huge data matrix. You usually factorize it at first. Mathematically, this looks really, really simple, as I said. So basically what you have the matrix V, you approximate it by multiplying W and H. So here's your matrix V. You have a lot of columns and a lot of rows. So, and this is then the factorization that you're interested in, which has a lower rank. So the matrix W, the column rank is lower than the column rank of V. And for H, you see that the row rank of H is lower than the row rank of V. And usually, so here you have a value K. So basically this shows you number of columns that you have for W. This is usually, for low rank approximations, much, much lower than the actual rank of V. Otherwise, it wouldn't make that much sense. And now when you have a look at individual elements of the different matrices. So let's have a look at the element of the matrix V at the second row, the first column. This is now the product of the second row of W and the first column of H. So very, very simple, right? So now you represent one entry of V by multiplication of a row and a column in another matrix. And this is the formula for that. So far you didn't gain anything from it, but this is just how it works. And probably even more importantly, what you can also do, or following from that, is that when you want to represent a complete column of V, you simply multiply the column of V. You can represent it by the matrix W multiplied by the first column of H. From that, you can see a few things. So the first is that somehow now you represented the first column of V by only the entries in H. So because this matrix W is just a new basis that you now use to describe your data in. So the matrix W now always stays the same. And for each of the different data samples that you have in V, which are in the columns, you now have a different set of coefficients which now describe this particular data sample. And this is then how it looks like. So basically you take the first row of H, multiply it by the first row, first column of H entry, and multiply it by the first column of W, and then you sum up the other values to it. Right. So from that you could already see that matrix factorization is nothing else as data transformation. So you take the data, transform it into something else, and then the outcome is, for example, this H, where you now have a completely different representation for the same data. And if you choose a lower rank, then you can also compress the data. So instead of having, for example, for this V, this large matrix, you now end up with this rather smaller matrix H. And this is the most common form, so you said V should equal the product of W and H. And for finding this kind of approximation, there now exists a broad range of different methods. So then you could also wonder, okay, why the hell are there so many different ways of approximating this matrix V? I mean, wouldn't it be sufficient to just have one of these methods, right? So just try to find a method that gives you the best possible approximation of V, assuming a certain rank that you want to achieve. But each of these different methods that are listed here, for example, k-means clustering, SVD, non-native matrix factorization, they all yield a different view, a unique view on the same data. So you always end up with sort of a different representation of the same data. And all these different representations have different benefits and are actually useful for different tasks. And therefore also that goal of approximating the matrix, it's not always really the goal of finding the best possible approximation. It's more the goal of finding the approximation that is most useful for the task at hand. So let's have a look, for example, at k-means clustering, which is obviously, on the first look, it's not really a matrix factorization approach. So it's most well known as a baseline clustering method, right? So when you want to apply k-means clustering, usually your task is you have a lot of data samples in some space, and you assume the data samples are Gaussian distributed. So then you say, okay, I'm looking for k clusters. Then you run k-means clustering, and the outcome of that is a couple of cluster centroids and the assignments of your data points to the different cluster centroids. So this is what k-means is doing. But if you can formulate it as a matrix factorization task, you will see that we have the same kind of formulation. So that's just V. Now, minus W times H. So this is a formulation. This is our objective function. So this is what we want to minimize. We want to approximate V as best as possible, but in the case of k-means, we impose certain constraints on the approximation. And the constraints are such that we say that H should be either 0 or 1, and that each column in H should sum up to 1. So what does that mean? So basically we impose a very, very hard constraint on this matrix factorization, and at the end, if you apply k-means, we end up with sort of a clustering of the data points. And for sake of completeness, so k-means is usually optimized using an expectation maximization schema. The optimal partitioning for k-means is NP-hard, so the problem is rather difficult, and the goal is to group similar data points. So why is k-means clustering matrix factorization? So let's have a look at this schematic view of it. So here you have the coefficient vectors h, so labeled here A. So what you see here, in each column, you have only all zeros, just one of the entries is 1. So what does it mean? We say we now want to represent our data samples by cluster centroids, and they should be assigned to exactly one cluster centroids. The cluster centroids are computed as a product of the matrix X and the matrix B. The matrix X now contains our original data set, original data samples, and the matrix B realizes a mapping of this original data set onto our set of k cluster centroids. So at the end, you end up with a matrix W that has in each column the cluster centroids and the matrix H where you have the assignment vectors. So this is why you can actually easily see that k-means clustering is nothing else than matrix approximation or matrix factorization. So basically, you always realize an assignment of data points X to a set of cluster centroids, right? And this is just by imposing these constraints and otherwise using that formula. So here you can see an example how that looks like for a set of facial images. So let's assume we want to approximate this particular facial image here by k-means partitioning or by a combination of basis vectors. So how would that look like? So we now have a couple of basis vectors here which correspond to these k-means cluster centroid vectors. And all of these are in the linear combination, all of them are 0, except for one, which is the one which is closest to the original data point that we put into this. And then we say, okay, we reconstruct it by just taking this one. So it's 1 multiplied by this guy here, and then you end up with sort of some representation of a facial image or some approximation of a facial image here. What you can also see for that k-means is for a lot of cases not really ideal, because here you can see, okay, this representation doesn't really look like a face anymore. It's sort of the mean of some, I don't know, different faces. But that's not the point. The point is only that you can easily can approximate or can express k-means clustering by matrix factorization, right? And so how would that look like in Python? So we developed in 2010 at the Fraunhofer Institute in Bonn and at the University of Bonn a little toolbox, PyMF it's called, for matrix factorization. And then we included a lot of different matrix factorization methods, also a lot that you cannot really find in other toolboxes. So k-means obviously not, I mean it's a very common method, I think. So the toolbox supports a vast number of different methods. It also supports HDF5 via H5Py and also sparse matrices. It doesn't support HDF5 and sparse matrices for all the methods. That has some technical reasons, and also sometimes for certain methods, even if you put a sparse matrix into it, you end up with a dense matrix, so therefore it doesn't really make sense to apply it there anymore. Anyhow, so how does it work? It's really, really simple. You simply create a matrix here, which is embarrassingly simple. It contains only 3 columns. Then you just apply the method to it, you set the number of iterations, and then at the end you can compute the approximation by having a look at the dot product of W and H, right? So, and one of the things that you also often would like to do is to map existing data onto the models that you have already computed, right? So this is also very, very common to do for clustering and matrix factorization and a lot of other of these tasks. And here it's also very, very simple. So what you do for your test data, you simply initialize a new k-means model. But now you submitted the test data, you set again the number of basis vectors that you would like to have. But then you assign the basis vectors that you computed before to just one of the basis vector of the test model. And then you just tell the factorization not to compute W at all. So basically you're just interested in optimizing for H. which is in that particular case the same as computing the distance of the data that you put into it to all the different basis vectors. But this, of course, can vary for different methods. And then at the end, you have an approximation of your test data using, or there you can also use, of course, the basis vectors that you have used before. Right, so that was about k-means clustering. As I said, there are a lot of different methods that are useful for different tasks. And k-means clustering is always used in the context when you want to group data, when you're interested, okay, how can I represent my data in such a way that I find data that, that belongs to a certain cluster region? Then you use k-means. Other methods, for example, PCA, I think is probably the most well-known matrix factorization method that exists, or SVD. And there, again, the task is almost the same. So again, you would like to find the best possible approximation of V by the dot product of W and H. But in the case of PCA, the restrictions are no different. So the constraints that you impose on the factorization, again, completely different. So here you say that W should be constructed out of the singular vectors of V, and the matrix should be orthogonal. So in principle, what you say, okay, you're looking for the eigenvectors, right? You want to find the best possible basis in order to represent V. So this is what PCA is doing. And then you don't have any constraint on the coefficient matrix H. So that can be non-negative, positive, it doesn't really matter, or negative. And exactly, so usually PCA violates non-negativity, so you cannot really control that. This makes it not really the ideal choice for data analysis. So as a data scientist, it's really a bit awkward. I mean, it's always only good for, in my opinion, for compression or for filtering out noise. That's when you usually would like to apply PCA. And also you can also see that when you have a look at the different approximations that you would get as the outcome of applying PCA to a facial image or a set of facial images. Here again we use PyMF, so the usage is exactly the same as before. You just switch the method, then you tell it to factorize, and then the approximation is again just the dot product of W and H. And here you can also see how the data approximation then looks like. So this is the facial image that you had at first, and then for PCA, I mean, usually what you get a pretty good approximation. This is simply because PCA is optimal. PCA or SVD will give you, for any rank K that you are looking for, it will give you always the most optimal data representation in sense of minimizing your objective function. But this does not mean that it is optimal in terms of interpretation, in terms of extracting valuable information from it. So for example, the basis vectors are usually not interpretable, which is a big disadvantage in data science. So you cannot assign any meaning to these basis vectors here. Another interesting and over the last years rather common method is non-negative matrix factorization. And again, you will see the basic form always stays the same, right? So I know we repeated that so many times. It's always the same. It's always V minus W times H. But this time again, you impose different constraints. Now you say, okay, I want to constrain W and H in such a way that they should be non-negative. And simply by imposing that constraint, you again end up with a completely different view on the same data. So completely different approximations and a different result also from in terms of when you want to interpret the data, right? So some details on NMF. There is said to be a global optimal solution to that, but there is no algorithm to actually find it. And the exact NMF problem is also NP hard. What is very interesting about NMF is that this non-negativity constraint, this results in sort of a part-based representation, or this often results in a part-based representation of your data, which is something which is also a bit unique, right? So for k-means clustering, you have the representation of these cluster centroids, then you can represent each data point by just one example data point. For PCA, you don't have anything, it's just sort of the most optimal representation. And now for NMF, you have a representation by parts. So now you can reconstruct your data by summing up different parts of your basis vectors. So let's have a look how it looks for the facial images here. So is that sort of visible? So there are also some other examples where the parts actually look a bit better. I think this is probably an artifact of the data set that I used here. But what you can see from that is that instead of now having some images which represent always the complete face or represent an individual, you end up with only parts of the face being available. So for example, here you could maybe say, so this is maybe the nose a bit, and here you have an ear. And then if you think about it, so now you are interested in a non-negative combination of these different parts. So you take 0 times this guy maybe, and here you have a nose, so maybe that's part of your image. So take maybe once this particular image, and then you have an ear. Okay, you might also want to have an ear, want to reconstruct an ear in your image. So then you can also put a certain amount of this image into the image, and at the end you end up with a fairly good approximation of your data set. But interestingly, when you then have a look at the coefficient vectors, you can always see, okay, I was using parts of this image and parts of this image, and if you can interpret these images, which you can often do, then you have pretty good understanding about what you're actually seeing here. So you can reconstruct data by individual parts which are sort of hidden in the data. Right, and the last example for these matrix factorization methods I want to talk about is called archetypal analysis. This, I believe, is really less well known. So it was developed in 1994 by Cutler and Bryman, and it's a fairly interesting method, I think, in terms of the outcome of the factorization of this. So the form mostly stays the same. So here's now a slight difference. So instead of just having W and H, you also incorporate the original data matrix V into this. So what does it mean? W is restricted to convexity. So that means all entries in W have to be larger or have to be non-negative, and each column needs to sum up to 1. So this is sort of a probabilistic combination of your input data points, right? And then for H, you have the same constraint. So it's also a convexity constraint. That means you restrict it to non-negativity, and then you also sum up, the columns have to sum up to 1. So that's again a probabilistic representation. So what is the outcome of this is that usually these archetypes, or the basis vector of this, are the most extreme data points. So for the facial images, you will end up, as you can also hear, first of all, what's interesting, you end up with actually existing images. So all these guys really exist in the database, and these are all images that we have in our data set. So that's the first interesting observation. The second interesting observation is that these images, the basis vectors, are the most extreme data points in the sense that they have the highest pairwise distance between them. So what does that mean? So when you have a look at the first 2 images, these 2 guys have the largest distance between them of all the images in the data set. So these are polar opposites, right? So you can think about it, if you would add more and more images to the data set that would show you all different kinds of human faces, you will at the end up with sort of the archetypical representations of human faces. And here, these guys are really extreme in the sense because this guy is rather pale, and here the lighting conditions maybe are not as good, so his skin color is rather dark. So what you see from that is that they're really polar opposite. And both guys don't have that much hair, right? So, which is also interesting. They even like their hair. And then it goes further. So these guys have a lot of hair here, and then it's also quite pale, quite pale skin. So what you can see from that. So, and the third guy actually also has sort of the highest possible distance to the first 2 guys. And then you take the fourth guy, and he's also having a very high distance to the others, right? So that's the first thing. So you end up with basis vectors that correspond to sort of the most extreme data points. The second interesting thing is you represent then your data. So the coefficient vectors, the H, are also restricted to convexity. So what does that mean? Basically, you now can represent each of your facial images that you have as a probabilistic combination of all these archetypes. So you can say with a probability of 0.35%, this guy is that guy, and with a probability of 0.2% that guy, and with a probability of 0.21%, it's the other one. So you're not saying that it is this person, but that it contains aspects of it. So this is a great tool for data analysis, because now you're able of representing data by something which is interpretable. So you can interpret these facial images. This is something that you cannot do with PCA, with k-means is also really, really difficult to do. And with NMF, okay, you have this part, which I think is also great. Now you can interpret data, and also you can represent data in a stochastic way, right? So these are probably the two most interesting things about that. And so overall, just to quickly summarize the different methods, right? So here you have again everything on one slide, and the list is actually much longer. So here I only mentioned the four most common methods. There are a lot more methods that can be easily expressed as a matrix factorization as a common form. And this also then obviously makes matrix factorization or low-rank approximations one of the most useful data exploration tools, simply because all these methods are low-rank matrix approximations. And here you can see it's also actually quite funny when you look at the list, right? So I never really checked, but I would assume that all possible constraints that you can impose on either of the matrices W and H somehow is manifested in a well-known method used for data analysis. So here you have no constraints, almost no constraints on W and H, so then you have PCA. I ignore sort of the orthogonality constraint simply because if you're looking for the most optimal representation for PCA, it will always be an orthogonal matrix. So that's just how it is. And then for k-means clustering, you have these two constraints. So you restrict H to 0 and 1, and it should the column should sum up to 1, right? So there's only one constraint, which is imposed on H, in fact. For NMF, it's non-negativity for both. And then for archetypal analysis, it's non-negativity and convexity. So it already has some parts of k-means clustering here. So you have for archetypal analysis, you restrict H, it should sum up to 1, like in k-means. And then you say, okay, it should be non-negative. This is like an NMF, right? So you can see this, all these methods are also somewhat related to each other, but they differ on the different constraints. And of course, the way they are optimized is also always different, right? So this is because different constraints actually facilitate different ways of optimizing them. And what's probably also important to note is that the tougher the constraint is that you impose, the more difficult it is usually to solve these approximations. So a lot of research also went over the last years into finding efficient approximations to archetypal analysis or NMF or other methods to make them useful or suitable for large data. And just quickly, as I spoke about large data, so at the beginning I mentioned that these PyMF, the Python Matrix Factorization Toolbox, also works with HDF5 or H5Py. It does, and the way it works with this is actually rather simple. So you can just use it the same way as you used it before. So you just so this is the function call here. So this is all the same. The only thing that you do, or that you have to keep in mind, is that you simply assign the matrices W and H. You have to initialize them first in a H5Py file, and then assign them before the factorization. Then PyMF realizes, okay, there is already a matrix, it's on disk, I will use that one, and then also keeps attention that not too much memory is consumed on the way. Again, it doesn't really work with all the methods, so there are still some methods that sort of suffer from that intermediate blow-up thingy, which often happens for a lot of these methods, that sometimes during the optimization, you have to do some matrix multiplication that will end up with really gigantic matrices. So while this is suited for doing matrix factorization for very large data, not all the methods are suited to it. And another example where we actually applied these things, so this was in 2010, we did some analysis on World of Warcraft guilds. So what we wanted to find out, okay, so what's the sort of social evolution of these skills? How do they change over time? Or can we find a representation of these skills that is sort of interpretable, that we can really analyze them? As you can think about, World of Warcraft was at that time actually a highly successful game. I think it's still, but it doesn't have that 12 million users as it used to be. And here we analyzed, I don't know, there's a number 192 million 70-dimensional data points or something like that. So it's quite some large matrix. I mean, obviously, nowadays you have much larger matrices, but this could also be easily done on a single machine without worrying too much. And although the data never fitted into memory, right? So, yeah, and as I said, so what we did apply here was actually an approximation of this archetypal analysis, which is called simplex volume maximization, which just delivers a really fast approximation to it, right? As a take-home message, effectively, a lot of methods in data analysis, so including clustering and so on, are nothing else as matrix approximation methods. They differ in the constraints that you impose on them. And interestingly, the constraints shape the outcome of these methods too. I mean, this is probably the most interesting take-home message. And in general, it's a super effective tool for data exploration. So there are a lot of methods, I mean, suited for, you know, when you're looking for a particular thing, there certainly is a data exploration way or a matrix factorization method for doing that. You won't always end up with something that is really super helpful, but a lot of these methods are, at least when you're dealing with data for the first time. And if you want to have a look at the Python implementation, you're of course very welcome. Thanks a lot for your attention, and questions are welcome.
So we have plenty of time for questions. Please ask away.
So PyMF seems to have quite an extensive library of matrix factorization algorithms. How fast is the implementation compared to other implementations?
Right. So the question is, if in PyMF, so it contains a lot of different matrix factorization methods, and the question is, how does the speed and performance compare to other methods? That's a good question. To be honest, for the standard methods, we never really measured. I think this is, I would assume other methods are more, other methods have a higher speed from other libraries. But what was for us more important was actually to implement the methods which do not yet have an implementation. But I would also be interested actually in measuring the speed and performance against other libraries, definitely.
Related question is, what's going on under the hood? Does it appeal to C or Fortran libraries to do fast numerics, or is it hard-coded in Python?
Yeah, the question was what is going on under the hood in PyMF, if it is using Fortran libraries and C libraries, or if it's using Python. And we mostly use NumPy and Fortran, which is basically like Park and Blast and all these things, obviously. So there is not much Python going on, so we don't have any for loops or everything is vectorized. So I think with respect to that, performance is probably quite good. And yeah.
Second question.
Sure.
Is any of it parallelized?
If it's parallelized, no, it's not parallelized. We had for some of the methods a parallel implementation running on Hadoop. But this was only for some other experiments we did. We never released that, but that might also be interesting for the future. Cool.
Yeah. In practice, also, we very often have tensors and NumPy arrays.
Right.
Matrices, right?
Sure.
So are you following the like tensor decomposition? It's a very active field, but are you looking at that for PyMF?
Yeah. The question was if we are in PyMF also using tensors. So a tensor is just a high-dimensional matrix. And in tensor factorization, so we also did some work on that in the past. We also considered it for PyMF, but we never really implemented anything because we also know that everything got so different once you go for a tensor. And as you also said, in NumPy, there is no good representation of a tensor. I mean, at least when I looked last time, which was 4 years ago. But I would be very interested in also hear more about that. But yeah, good question. No? Yeah.
So this all seems to be L2 loss-based, which is not so good for if you want recommendation systems or something like that, because usually you have implicit feedback, and L2 is not a great loss for that. Also, you often have binary matrices. So have you also looked into other losses?
Okay. The question was if we had to look at other loss functions apart from the simple Frobenius norm that we're usually using. To be honest, not really. I recently supervised a master thesis on S3D++, which would be a recommendation matrix factorization method, and they're using, I'm not really sure actually, they use, I think, the same loss function, but some other regularizations. But honestly, no. I have more questions.
Okay, if there's no more questions, let's thank Christian once again.